what if the very tools designed to secure and grant access to your cloud environment, like your IAM roles and your cryptographic signing keys, what if they become the exact weapons used to dismantle it? As a security professional, how do you defend an infrastructure when the identity provider itself is compromised?
I mean, it is the ultimate nightmare scenario, right? When the foundation of trust is broken at that provider level, or when your identity perimeter just collapses, everything built on top of it crumbles. You can have the most sophisticated firewalls in the world, but if the attacker's holding the master keys, well, the system just sees them as a VIP.
Yeah, that's exactly where we are going today. If you are a cloud architect or a SOC analyst or a security engineer listening right now, we know you are dealing with alert fatigue. We know you are staring down endless compliance audits.
Yeah.
And we absolutely understand the constant low-level anxiety of managing misconfigurations in these, dynamic multi-cloud environments.
Oh, the burnout in the security operations center is incredibly real. We hear it all the time.
It really is.
Yeah.
So today we are skipping the high-level fluff. We are getting deep into the weeds.
Right.
We're going to tear apart the postmortems of massive real-world cloud breaches, specifically Capital One, the Microsoft Storm 0558 espionage incident, and the 2024 Snowflake extortion campaigns, to see exactly how clouds actually break in the real world.
Right. And then we are putting AWS, Azure, and Google Cloud Platform head-to-head in a highly technical showdown.
Exactly. And finally, we are dropping down into the Linux kernel to see how the eBPF revolution is fundamentally rewriting the rules of runtime security.
It's an aggressive agenda, but honestly, to actually defend these environments, we have to look beyond the vendor marketing material. We need to transition from the theory of cloud security to the harsh reality of practice. And to do that, our research breaks down cloud failures into three distinct architectural archetypes. You have a customer configuration failure, a systemic provider failure, and an identity or supply chain failure.
So let's start with that first archetype, right? The configuration failure. I want to look at the 2019 Capital One breach. And I know it's a few years old, but it remains the absolute textbook case study that every cloud security professional needs to understand at a forensic level.
Oh, absolutely. It's foundational.
Right. So in 2019, a former AWS engineer named Paige Thompson stole the personal information of over 106 million Capital One credit card applicants. We were talking names, addresses, dates of birth, self-reported income, and credit scores.
And the blast radius of this was just enormous, both technically and, well, financially. Over $270 million in fines, including an $80 million penalty from the Office of the Controller of the Currency alone.
Wow, $80 million just from the OCC.
Yeah, exactly. The OCC audit process following that breach completely reshaped how financial institutions are required to manage cloud risk. But the technical vector is what's truly fascinating to me, because it was a chain of seemingly minor missteps that compounded into a complete catastrophe.
Yeah, let's get into the mechanics of that vector. The initial entry point was a server-side request forgery, or SSRF, vulnerability in a web application firewall, a WAF, that Capital One had deployed on an Amazon EC2 instance. And just to be clear on what an SSRF is for you listening out there, she basically found a loophole where she could trick the firewall itself into making outbound web requests on her behalf.
Right, she used the firewall as a puppet, basically.
Exactly, a puppet to talk to internal systems that were supposed to be completely hidden from the outside world.
That is the perfect way to frame it. I mean, a firewall's job is to inspect incoming traffic, maybe drop some malicious packets, and then route the safe traffic to the back end, right? It sits right at the edge of the network. But an SSRF vulnerability flips that entire dynamic.
How so?
Well, if an attacker can manipulate the URL or the parameters that the solver uses to fetch data, they can force the server to send an HTTP request to an internal, non-routable IP address. The server is basically saying, sure, I'll go grab that data for you, without realizing it's reaching into its own highly restricted internal network.
And in an AWS cloud environment, the absolute most lucrative internal resource you can hit with an SSRF attack isn't a database. It's the Instance Metadata Service, or IMDS, right?
Oh, yes. For those of you managing AWS environments, you know this IP address by heart. It's 169.254.169.254.
The magic number.
The magic number is exactly. It is a link local address, so it doesn't go out to the internet. It is intercepted by the virtualization hypervisor layer that's running the EC2 instance. The IMDS provides compute instances with data about themselves, things like their instance ID, their network interfaces, and crucially, the temporary security security credentials for the IAM role attached to that specific instance.
And this is where the specific architecture of the time becomes so critical. Capital One was using IMDS version 1, and IMDS v1 was, well, it was incredibly permissive by design, wasn't it?
It really was. It was designed for ease of use, which, in security is very often the enemy of defense. IMDS v1 responded to simple HTTP GET requests. So if an attacker could execute an SSRF vulnerability on that wave application, they didn't have to jump through any complicated hoops.
They just asked for the keys.
Literally. They just told the WAF application to send a standard GET request to that 169.254 address, specifically to the latest metadata IAM security credentials path. The hypervisor intercepted that request, looked at it, saw that it was originating from the EC2 instance itself, and happily handed over the temporary IAM tokens.
So the hypervisor doesn't know there's an attacker sitting on the other side of the world pulling the strings. It just sees the wave asking for its own keys.
Yeah.
I always think of IMDSV1 like a receptionist handing out vault keys to absolutely anyone wearing a company badge.
That's a great analogy.
Right. As long as you are physically inside the building or, inside the EC2 instance, the receptionist doesn't ask any questions. But AWS responded to this breach by heavily pushing IMDSV2, which changes the mechanics completely.
And it was a massive architectural shift. IMDSV2 requires a session token. It's not just a simple GAT request anymore. To get those temporary credentials now, the EC2 instance first has to send a specific HTTP PUT request to generate a token. And this PUT request requires a very specific custom header.
The XAS EC2 metadata token 30 seconds header.
Exactly that one.
And that custom header is basically the kill switch for SSRF, isn't it? Because an attacker exploiting a basic URL parsing flaw usually can't force the server to inject custom HTTP headers into that outbound request.
Precisely. It breaks the attack chain. And furthermore, once you get that token, you have to include it as a header in all subsequent GAT requests. AWS also added network-level protections. The packets generated for IMDS v2 have a time to live, or TTL, of exactly 1.
Wait, a TTL of 1, so it can't be routed at all.
Exactly. This means the packet cannot be routed through another proxy or network hop. It will simply expire and be dropped. So a standard SSRF attack usually cannot generate these complex multi-step requests with custom headers, and even if it somehow could, the TTL restriction prevents the metadata from being forwarded back. It effectively neutralizes the vulnerability.
But getting the credentials to the web application firewall is only half the story here.
Yeah.
As you mentioned earlier, a firewall's job is edge routing and inspection. It shouldn't have access to the actual sensitive customer data sitting in storage in the first place.
Right, and this is the second catastrophic failure, and it's something SOC analysts deal with every single day. It's the over-permissioned identity and access management roles. The IAM role attached to that specific EC2 instance was called ISRM WAF role. And for some reason, this role had permissions to execute S3.list buckets and S3 get object commands across more than 700 S3 buckets in the Capital One environment.
That is just wild to me. I mean, functionally, why would a WAF ever need read access to 700 storage buckets containing credit applications?
It wouldn't. It absolutely shouldn't. This is a classic catastrophic violation of the principle of least privilege. But, let's express some empathy for the engineers here, because we know exactly how this happens in the real world.
Oh, for sure. The pressure to ship is real.
Exactly. Developers and infrastructure teams are under immense pressure to deploy. They are building complex applications, and they run into access-denied errors. To bypass the friction and just get the pipeline moving, they attach a broad AWS-managed policy like Amazon S3 read-only access just to make things work.
And they say they'll fix it later.
Always. They plan to scope it down later. They tell themselves they'll look at the CloudTrail logs next week and narrow down the IAM policy to just the specific buckets the WAF needs. But as we all know, later never comes.
Technical debt is just security debt waiting to be cashed in, and Paige Thompson cashed it in. When she had those temporary credentials, the access key ID, the secret access key, and the session token, she simply exported them to her local environment.
Yep, she took them completely offsite.
Right, she used a standard AWS command line interface from her own machine, completely bypassing the way at that point, and just ran an Oz S3 sync command to drain the buckets.
It's a very sobering reminder of the shared responsibility model. AWS provided secure infrastructure. The hypervisor worked exactly as it was programmed to work, but Capital One failed to secure their firewall application, and they failed to scope their IAM roles. They owned the configuration, and the configuration failed.
Okay, so Capital One is our baseline for what happens when a customer misconfigures their own environment. But let's shift our perspective to something much more terrifying for a moment. What happens when the customer does everything right? They have perfect IAM hygiene, MFA is enforced, their firewalls are patched, but the cloud provider themselves suffers a systemic collapse.
That is the stuff that keeps CISOs awake at night.
Exactly. This brings us to the second archetype. The 2023 Microsoft Exchange breach by the Chinese Advanced Persistent Threat Group, tracked as Storm 0558.
This is one of the most significant and, frankly, structurally alarming espionage incidents in recent history. Storm 0558 managed to access the email accounts of approximately 25 highly sensitive organizations, including the U.S. State Department and the Department of Commerce.
And they didn't do it by phishing, did they?
No, they didn't do it by phishing employees, they didn't guess passwords, and they didn't find an open S3 bucket. They did it by forging cryptographic authentication tokens.
They literally minted their own access passes. Let's break down the math and the architecture of how that is even remotely possible.
Yeah, to understand the magnitude of this failure, we have to look at how modern federated authentication actually works. When you log in a Microsoft 365, the Azure Active Directory identity provider validates your credentials. If you pass, it issues you a JSON Web Token, a JWT, typically structured as a SAML or OAuth token.
Right, and that token contains your claims.
Exactly. It contains your username, your roles when the token expires. But, anyone can create a JSON file. To prove that Microsoft issued it, the token is digitally signed using asymmetric cryptography.
The public key infrastructure.
What?
So Microsoft signs the token with a highly guarded private key.
Yes, and when you present that token to the downstream service like Exchange Online or Outlook Web Access, that service checks the signature. It looks up Microsoft's published public key, performs a cryptographic validation against the token's signature, and if the math checks out, the service grants you access.
So the entire Zero Trust architecture relies on that key.
The entire Zero Trust architecture of the modern internet relies on the absolute secrecy of those private signing keys.
So the keys to the kingdom aren't passwords anymore. They are the cryptographic signing keys.
Exactly. And Storm 0558 somehow acquired an MSA, a Microsoft Account Consumer Signing Key. This is a private key specifically designated for consumer services. Think like Xbox Live or personaloutlook.com accounts.
Wait, hold on. Let me stop you there. If they acquired a consumer key designed for Xbox or free Outlook account, how does an enterprise government mail server even accept that? Doesn't the cryptographic validation process immediately look at the key ID, realize it's consumer key, and just throw it out?
It absolutely should have. And that was the fatal systemic flaw on Microsoft's end. It wasn't just that a key was stolen, it was a cascading failure of validation logic. There was a token validation error deeply embedded in the Microsoft 365 code base.
So the enterprise systems were just blind to the key type.
Basically, yes. The enterprise mail systems, specifically the API endpoint called Get Access Token for resource, were failing to properly differentiate between tokens signed by enterprise Azure AD keys and tokens signed by consumer MSA keys.
Oh, wow.
Yeah, the validation logic essentially just checked the mathematical signature, saw that it was signed by any valid Microsoft key in their broader registry, and said, well, the math works, come on in.
That is mind-blowing. An enterprise system trusting an Xbox key.
But let's go back to the theft itself.
Yeah.
How does a highly guarded cryptographic private key fall into the hands of a Chinese APT in the first place? The forensic trail is fascinating, honestly. The key they stole was highly legacy. It actually hadn't been actively rotated since 2016. According to Microsoft's official postmortem, a race condition occurred during a system failure in the highly secured air-gapped production environment.
Okay, so a crash happens.
Right, a crash happens. And this system crash generated a memory dump, a .demp file containing the raw contents of the server's RAM at the moment of failure.
And cryptographic keys are held in RAM when they're actively being used to sign things.
Yes. So the key material leaked into this corporate crash dump. Now, standard procedure is that crash dumps from production should have sensitive material scrubbed before being moved anywhere else. But a separate flaw in the scrubbing mechanism failed to detect the key material.
Oh no, a cascading failure.
Exactly. This unscrubbed crash dump was then transferred from the lockdown production environment into a much less secure, internet-connected corporate debugging environment so engineers could, investigate the crash.
The blast radius just keeps expanding.
It does. The threat actor, Storm 0558, managed to compromise a Microsoft engineer's corporate account. They used that access to pivot into the debugging environment, scoured the stored crash dumps, identified the memory pages containing the private key, and simply extracted it.
That brings up a terrifying point for the security teams defending these networks. If the identity provider itself, the literal foundation of your zero-trust architecture, is issuing valid, mathematically sound tokens to attackers, how on earth do you detect it? I mean, your tools are going to see a perfectly valid login.
It is incredibly difficult, and it relies entirely on deep behavioral telemetry. You cannot rely on static signatures for this. The U.S. State Department only caught this intrusion because they were deeply analyzing their mail item access pattern.
What were they looking for exactly?
They noticed anomalous access, specifically the mail items accessed event, that didn't correlate with their known user behavior. They dug into the granular token metadata, specifically looking at the key ID, and realized these enterprise sessions were being authenticated by an unfamiliar key ID that belonged to the consumer infrastructure.
And the attackers knew they had to blend in, right? Our research notes they used dedicated soft ether VPN proxies to mask their token replay attacks.
Yes, SoftEther is an open-source, highly capable multi-protocol VPN software. The APT didn't just blast these forged tokens from known malicious IP addresses in China. They carefully routed their traffic through compromised residential and commercial proxies across the globe.
Trying to bypass conditional access?
Exactly. They were specifically trying to bypass conditional access policies that block logins from foreign countries. They wanted their API calls to Outlook web access to look like a US-based diplomat checking their email from a hotel or a domestic internet service provider.
And this specific detection methodology by the State Department sparked a massive industry-wide controversy regarding what we now call the logging tax.
Yes. This is where the technical failure becomes a major policy issue. The State Department was only able to see those mail items accessed events because they had paid Microsoft for the premium logging tier, known as Purview Audit Premium.
And the other organizations.
Other targeted organizations who had only paid for standard licensing had absolutely no telemetry to detect this breach. They were completely blind to the fact that their emails were being read by a nation-state.
That is a harsh reality. If you don't pay the toll, you don't get the visibility.
Yeah. But the industry pushed back hard on this, didn't they?
Extremely hard. The Cyber Safety Review Board, the CSRB, which is a group of government and industry experts convened by the Department of Homeland Security, released a blistering 34-page report on this entire incident. They fundamentally blasted Microsoft's security culture.
I read some of that report. It was brutal.
It was. The report explicitly stated that security-related logging is a control floor, not an upsell feature. You cannot charge customers extra for the basic foundational telemetry required to detect an intrusion in your own platform.
And to their credit, or perhaps due to the immense regulatory and public pressure, Microsoft did pivot. They subsequently made standard Purview audit logging free for all customers, increasing the default retention and expanding the event types available. They did. And they also dramatically expanded their Secure Future initiative, completely overhauling how they manage identity keys. They were moving to purely hardware-backed signing keys inside HSMs and automated key rotation enforcement, so a key sitting in a crash dump from 2016 can never, ever be used again.
It was a painful, highly public reckoning for the entire industry. It proved that systemic provider failures are rare, but when they happen, the blast radius is global. But we cannot let provider failures distract us from the most common threat vector. As we move forward in our analysis, we have to look at the third archetype, the identity and baseline failure. Let's examine the 2024 Snowflake breaches.
Right, this one dominated the headlines all summer. The threat actor, tracked by Mandiant as UNC 5537, targeted massive Snowflake data warehouse customers. We are talking about hundreds of millions of records exfiltrated from companies like AT&T, Ticketmaster, Santander, and Advance Auto Parts.
But what's fascinating here, and crucial for you SOC analysts listening to understand, is that the attackers didn't exploit a zero-day vulnerability in Snowflake's infrastructure. They didn't forge cryptographic keys like Storm 0558. They didn't even need a WAF misconfiguration.
No, not at all. This was an attack on the fundamental access layer. It was a failure of basic identity hygiene. The attackers utilized InfoStealer malware.
Let's dive deep into InfoStealers because this is becoming the absolute bane of enterprise security. How do these tools actually work?
Well, malware families like Redline, Raccoon Stealer, or Luma Stealer are designed for one specific purpose, and that's rapid, silent credential extraction. They typically infect a user's machine, very often a contractor's personal unmanaged laptop via a phishing payload, or disguised as pirated software or maybe malicious browser extensions.
And once they execute, what are they targeting? Just files?
No, they target the local storage of web browsers. Browsers like Google Chrome or Microsoft Edge use a localized Swiss-like database, often called login data, to store your saved usernames and passwords. They also store your active session cookies in a very similar database.
But those are encrypted by the OS, right?
They are. On Windows, they use the Data Protection API, or DEEP API, tied to the user's local account. But because the malware is running under the context of that logged-in user, the malware can simply ask the operating system to decrypt the database, and the OS just complies.
So the malware silently scrapes every saved password, every active session cookie, zips it up, and exfiltrates it to a command and control server. Then, these threat actors package these logs and sell them on dark web marketplaces like Russian Market or Too Easy.
Exactly. And UNC 5537 simply bought or acquired these logs. They sifted through them looking for URLs ending in snowflakecomputing.com. And when they found valid usernames and passwords, they just logged in.
Which brings us back to the shared responsibility model. If this was just a case of stolen passwords via commodity malware on a contractor's personal laptop, why is this categorized as a cloud breach? Snowflake isn't responsible for a contractor's laptop.
You're right. Snowflake, as the cloud provider, properly secured their backend infrastructure. There was no breach of the Snowflake platform itself. Their hypervisors, their storage buckets, their API gateways were all operating securely. However, the customers failed to secure their data access layer.
They lacked MFA.
Exactly. The accounts that the attackers compromised lacked basic multi-factor authentication.
That is just staggering in 2024 to have enterprise data warehouses containing millions of highly sensitive customer records accessible with just a username and a password. No MFA. No conditional access policies restricting logins to known corporate VPN IP addresses. Just a password.
It highlights a massive blind spot in cloud adoption. Many organizations assume that because they are using a modern SaaS-based cloud platform, the security is inherently, taken care of. But Snowflake operates heavily on identity federation.
Right, if you leave the front door unlocked.
Exactly. If you fail to mandate MFA in your identity provider policies, the strength of the vault inside doesn't matter. The attackers simply authenticated via the Snowflake web interface or the SnowSQL command line tool, ran massive select asterisk queries, and downloaded terabytes of data.
And that led to some brutal extortion demands.
Very severe, with some victims paying upwards of $2 million in illicit gains just to stop the data from being leaked to the public.
Okay, let's synthesize this. These three architectural failures really map the modern threat landscape for us. Capital One taught us that an SSRF paired with an over-permissioned IAM role is a fatal combination. Storm 0558 showed us that even the cryptographic foundations of identity providers can shatter, making deep anomaly-based telemetry an absolute necessity. And Snowflake reminded us that advanced cloud platforms are utterly trivial to breach if you don't enforce baseline identity hygiene like MFA and conditional access.
And knowing exactly how these environments break sets the stage perfectly for our next analysis. If you are a cloud architect tasked with defending against these exact scenarios, which provider gives you the best tools to do it?
Right. It's time for the 2026 Hyperscaler Showdown. We are putting Amazon Web Services, Microsoft Azure, and Google Cloud Platform head-to-head. We're going to grade them across several highly technical security domains based on our extensive research. So let's start with the absolute foundation, identity and access management and network security.
So across the board, the research largely declares a tie between the big three in these foundational categories. IAM is the bedrock of any cloud provider. AWS utilizes its JSON-based IAM policies, which are incredibly granular. You can specify exact actions, resources, and conditions.
And Azure.
Azure utilizes role-based access control, or RBAC, deeply tied to Azure Active Directory, now called Entra ID, which provides phenomenal hierarchical management across management groups, subscriptions, and resource groups. GCP uses a similar IAM binding model, linking members to roles at the organization, folder, or product level.
And on the networking side, same story.
Basically, yeah. The primitives are all there. You can build virtual private clouds in AWS and GCP, or virtual networks, VNets, in Azure. You can implement granular microsegmentation using security groups in AWS or network security groups in Azure.
You can enforce strict ingress and egress rules.
Right. If you can't get IAM and networking right, you can't operate a hyperscale cloud. The differentiation isn't really in the existence of these tools, it's in how they are managed at scale.
And that brings us to where things get really intriguing. Cloud Security Posture Management, or CSPM. This is the tooling that continuously scans your environment to find the exact kind of misconfigurations that led to the Capital One breach. It looks for public S3 buckets, missing encryption, or over-permissioned roles. So who wins the CSPM category?
Based on the research, it indicates a tie between Microsoft, Azure, and Google Cloud Platform, leaving AWS slightly behind.
Wait, I have to push back on that a bit. AWS Security Hub is a massive, widely used platform. I mean, it aggregates alerts, it runs continuous compliance checks against CIS foundations, and it integrates with almost every AWS service. Why doesn't AWS take the crown for posture management?
It really comes down to the reality of modern enterprise architectures. AWS Security Hub is an exceptionally powerful tool. Under the hood, it leverages AWS config to track resource changes and evaluate them against managed rules. But it is deeply, fundamentally AWS-centric.
Ah, I see.
Yeah, it provides a phenomenal centralized view of your posture within the AWS ecosystem. However, in 2026, single cloud deployments are increasingly rare. Most large organizations operate in heavily fragmented multi-cloud environments.
That's very true. Due to mergers, acquisitions, or just different engineering teams having different preferences, a company might have their core compute in AWS, their massive data lakes and machine learning pipelines in GCP, and their entire corporate identity and productivity suite running on Azure.
Precisely. And this is where Azure excels. Microsoft Defender for Cloud, specifically its CSPM capabilities, is designed from the ground up for multi-cloud visibility. Through Azure Arc and native cloud connectors, it actively ingests posture data from AWS and GCP without requiring massive custom engineering.
So it maps the cross-cloud risk.
Yes, it provides attack path analysis that can map an identity risk in Azure AD that could be exploited to compromise an AWS EC2 instance. GCP Security Command Center also offers very strong centralized risk management, particularly excelling in organizational policy enforcement, which keeps it tied at the top. But Azure's seamless, out-of-the-box multi-cloud integration gives it a significant edge over AWS in this specific multi-cloud reality.
That makes total sense. If your CSPM only sees 1/3 of your infrastructure, you have a massive blind spot. An attacker only needs one misconfigured gateway in your secondary cloud to pivot. So let's move to threat detection and monitoring. This is the dynamic layer. This is the capability you need to catch active exploitation, like the Storm 0558 token forgery. How do the big three compare here?
Here, the landscape is heavily specialized based on your organization's operational model. AWS shines for deep infrastructure monitoring with Amazon Guard Duty. Guard Duty is brilliant because it doesn't require deploying agents.
Right, it just consumes the logs.
Exactly. It natively consumes massive streams of AWS data VPC flow logs, DNS query logs, CloudTrail management and data events, and EKS audit logs. It applies machine learning models to detect anomalies like cryptocurrency mining, unusual data exfiltration, or compromised EC2 instances talking to known command and control servers.
And they added generative AI to it recently, right?
They did. Recently, AWS integrated Amazon Bedrock Security, leveraging generative AI to provide automated incident response recommendations and to summarize complex alerts for junior analysts.
But Azure takes a completely different angle here. Right?
Yeah.
They lean heavily into the security information and event management, the SIEM side.
Yes. Azure integrates Microsoft Defender with Microsoft Sentinel, which is their cloud-native SIEM. This is the absolute best choice for enterprise ecosystems that are already heavily reliant on Windows endpoints, Office 365, and Active Directory.
Because it's all in one ecosystem.
Right. Sentinel uses Custo query language, which is incredibly fast for parsing massive datasets. The integration means an alert on a user's Windows 11 laptop in Defender for Endpoint is instantly correlated with an anomalous login in Entra ID and a suspicious file download in Azure Storage.
And Copilot fits in there too.
Exactly. The addition of Microsoft Security Copilot gives analysts an LLM interface to rapidly query this entire ecosystem, asking questions in natural language and getting complex KQL queries executed in the background.
I imagine Google takes a completely different angle here, given their obsession with massive data analytics and AI. Do they just throw all this telemetry into a massive data lake?
That is exactly their approach. GCP leverages Chronicle Security Analytics. Chronicle completely rethinks the SIEM model. Instead of paying exorbitant ingestion fees per gigabyte, Chronicle is designed to ingest massive petabyte-scale telemetry at a fixed cost.
Oh, that fixed cost model is huge for budgeting.
It changes everything. It normalizes this data into a unified data model. It then applies Google's own internal threat intelligence, the exact same intelligence that protects Gmail and Google Search, to hunt for threats at an unprecedented scale using YARA rules.
So Vertex AI is running on top of that.
Yes. Coupled with Vertex AI Security, GCP is the go-to platform for organizations prioritizing proactive threat hunting, highly advanced data science-driven security models, and deep zero-trust architectures.
So it's a three-way tie, but the winner really depends on your DNA. If you are infrastructure heavy, you go AWS. If you are an enterprise Microsoft shop, go Azure. If you want to build custom data science models on petabytes of logs, go GCP.
Exactly. You have to align your security tooling with your engineering culture.
Let's shift to key management and encryption, protecting the actual data at rest. There is a bit of a contradiction in the research here regarding GCP that we really need to unpack. One analysis explicitly states that GCP lacks dedicated hardware security modules, or HSMs, while another concludes that all three providers offer robust key management and HSMs if required. As an auditor, how do we reconcile that discrepancy?
Yeah, it comes down to a nuance in architectural philosophy and how the services have evolved over time. Historically, GCP focused heavily on software-based key management. Their philosophy prioritizes a model where they encrypt absolutely all data at rest by default, using Google-managed encryption keys.
So no configuration required.
Right. A developer doesn't have to configure anything. The data is encrypted at the storage layer automatically. This is fantastic for a privacy-first, zero-configuration baseline. However, for organizations with incredibly strict regulatory requirements, like the Department of Defense or highly regulated financial institutions, software keys just aren't enough.
They need the physical hardware.
Exactly. They demand dedicated physical hardware security modules that meet FIPS 140-2 Level 3 compliance. These are physical devices with anti-tamper mechanisms. If someone tries to drill into the server chassis to extract the keys, the device physically destroys the key material.
Right. And AWS Key Management Service and Azure Key Vault have traditionally offered deeply embedded, highly mature cloud HSM offerings for those exact use cases.
Exactly. AWS KMS is the gold standard for granular, large-scale cryptographic control. You can implement customer-managed keys, define incredibly complex key policies, and utilize envelope encryption, where a data encryption key is encrypted by a key encryption key stored in the HSM across almost every single AWS service.
And Azure?
Azure Key Vault excels in integrating key management not just for cloud resources, but for hybrid enterprise tools and application secrets. While GCP has closed the gap significantly and does offer cloud HSM and external key management services now, AWS and Azure still hold the maturity edge for strict hardware-backed compliance. But, GCP still wins for organizations that just want pervasive encryption without the administrative overhead of managing key rotation schedules.
And speaking of regulatory requirements, let's look at the final category in our showdown. Compliance frameworks. Managing FISMA, HIPAA-CAT, PCI DSS, SOC2, and the massive new European Digital Operational Resilience Act, or DORA, across a fragmented multi-cloud environment sounds like an absolute nightmare for governance, risk, and compliance teams.
Oh, it is arguably the single biggest headache for a modern CSO. Proving compliance is often harder than achieving security, and all three providers offer strong continuous compliance tools to automate the generation of audit evidence. AWS has AWS Artifact to download compliance reports and AWS Audit Manager to map your infrastructure to specific controls.
And Azure and GCP.
Azure uses Azure Blueprints and Azure Policy to enforce compliance guardrails at the point of deployment. GCP relies on assured workloads.
So who takes the crown for GRC?
It's another tie, but again, specialized by use case. AWS leads the pack in global broad certifications. If you operate a multinational corporation and need to prove compliance against dozens of different global, federal, and industry-specific standards simultaneously, AWS has the most extensive, mature library of certifications and automated audit mappings.
What about Azure?
Azure differentiates itself with regional compliance and data sovereignty. If you operate in a jurisdiction with strict data localization laws, meaning the data must physically reside within the borders of a specific country and can only be accessed by citizens of that country. Azure's localized compliance tools and their vast footprint of regional data centers are incredibly strong.
And GCP?
GCP leans heavily into privacy syndicate frameworks like GDPR in Europe and CCPA in California. Google Assured Workloads is fantastic at automatically applying platform-level controls to ensure data never leaves a specific geographic boundary and is only supported by vetted personnel within that region, heavily utilizing their external key management to ensure even Google cannot access the data.
Okay, so the hyperscaler showdown reveals a pretty complex reality. There is no single best cloud for security. It is highly dependent on your architecture. AWS for deep infrastructure control and global compliance scale. Azure for multi-cloud CSPM visibility and enterprise SIEM integration, and GCP for AI-driven analytics, zero configuration encryption, and strict privacy boundaries.
But here is the critical pivot, and this is something every security engineer listening needs to internalize. None of these tools, not the CSPMs, not the AI-driven SIEMs, not the advanced threat detection models, mean absolutely anything if they don't have high-quality data to analyze. Tools are entirely useless without the underlying telemetry.
Yes, absolutely. You can buy the most expensive security dashboard in the world, complete with generative AI and 3D attack path mapping. But if it's not ingesting the right logs, you are just flying blind. To detect a slow, methodical anomaly like the Storm 0558 token forgery, or to retroactively audit the Capital One bucket enumeration, your SOC analysts need high-fidelity, normalized logs. Which brings us to part 3, the telemetry lifeline.
This is where the real daily battle of cloud security is fought. It's in the logs. And to understand cloud logging architectures, we must clearly, unequivocally define the difference between control plane logging and data plane logging. This distinction dictates your storage costs, your query performance, and your blind spots.
The key distinction here, which always causes headaches in billing and monitoring, is the split between configuring the cloud versus actually using the cloud. The control plane is the management layer. It's where you make administrative decisions via the cloud provider's API gateway, when you create a new virtual machine, when you modify an IAM policy, when you alter a route table, or when you open a port on a security group. Those are control plane actions. You are telling the cloud how to behave.
Right, and the data plane is where you interact with the actual resources themselves. When an application executes a SQL query against a managed database, when a user downloads a gigabyte of data from an S3 bucket, or when a network packet physically flows through a load balancer, those are data plane actions.
So going back to our breach archetypes,
Yep.
in the Capital One breach, modifying the IAM policy to give away excessive permissions was a control plane action. But the attacker actually running Oz S3 sync and downloading 30 gigabytes of credit applications, that was a data plane action.
Precisely. And tracking both is incredibly resource intensive, but data plane volume is orders of magnitude larger. Let's look at how AWS handles this with AWS CloudTrail. By default, CloudTrail only records management events, so the control plane. It tells you who created a bucket or who modified a role.
But not who read a file.
Exactly. By default, it does not log data events like an individual GetObject API call reading a file in S3. If it did, a heavily utilized S3 bucket serving web assets would generate billions of log entries a day, and the storage costs would literally bankrupt you. You have to explicitly manually enable data event logging for your most sensitive resources.
And traditionally, CloudTrail retains those logs in the console for 90 days. But 90 days isn't enough for advanced persistent threats who often lurk in environments for months before exfiltrating data. Our research highlights a massive upgrade here, AWS CloudTrail Lake.
CloudTrail Lake completely changes the forensic investigation timeline. It allows you to store immutable event data for up to 10 years. But more importantly, it solves the query problem. Traditionally, if you wanted to search 5 years of CloudTrail logs, you had to export massive, nested JSON files to S3, set up Amazon Athena, define complex schemas, and then run queries.
Which is a nightmare.
It is. CloudTrail Lake natively lets you query those logs using familiar, fine-grained SQL syntax right inside the AWS ecosystem.
How does Azure handle this massive split between management and data?
Azure utilizes Azure Monitor and routes security data into a log analytics workspace, or LAW. They separate this telemetry into activity logs for the control plane tracking who, what, and when for subscription-level events, and resource logs for the data plane. But Azure's true superpower here, as we mentioned during the SIEM discussion, is the Custo query language, KQL.
I'm a huge fan of KQL. It just feels so much more intuitive for time series data than traditional SQL.
It really is. The research consistently ranks Azure and GCP as winners for logging specifically because of their querying power. KQL is designed specifically for massive data sets. It uses a piped syntax where you take a data set, filter it, summarize it, and project the results step by step.
It's very clean.
Very clean. It allows analysts to parse JSON fields, correlate different log sources, and visualize threat hunting data much faster than fighting with complex SQL join statements.
And GCP has cloud audit logs, which elegantly categorizes things into admin activity, data access, system events, and policy denied logs. And because it's Google, you just stream that directly into BigQuery, and you have the power of Google's planetary scale analytics engine to run SQL across petabytes of logs in seconds.
Exactly. But there's a massive operational challenge here that breaks security teams. If you are in a multi-cloud environment, you are staring at a nightmare of formatting. You have CloudTrail logs in highly nested JSON. You have Azure Activity logs in a completely different JSON structure. You have GCP audit logs formatted as protocol buffers or protobufs.
And the naming conventions are all different.
Exactly. They all use different naming conventions. AWS calls it an instance seed. Azure calls it a resource seed. They use different timestamp formats. How do you correlate a threat actor compromising an AWS IAM credential and then using that to pivot into your Azure Active Directory?
Writing parsing rules for that is an absolute regex nightmare. Every time a provider updates their log format, your Simon Just rules just break. You need a Rosetta Stone. You need to normalize the data before you analyze it.
And that is exactly where the Open Cybersecurity Schema Framework, or OCSF, comes in. This is arguably one of the most important open source initiatives in cloud security right now. Backed by heavyweights like AWS, Splunk, IBM, and CrowdStrike, OCSF is standardizing the language of telemetry.
So it does the mapping for you.
Yes. Instead of writing 3 different brittle parsing rules to understand a basic user login event across 3 clouds, OCSF defines a vendor-agnostic taxonomy. The log data is normalized into a single standard schema, mapping the source IP, the user identity, the action, and the outcome into consistent fields before it ever hits your SIEM or data lake.
That saves hundreds of hours of engineering time just maintaining ingestion pipelines. But standardizing the logs is only step 1, right? How we actually act on them is shifting entirely. The research points to a major transition away from periodic scanning toward event-driven drift detection.
This is a critical paradigm shift for catching misconfigurations before they are actively exploited. In the past, a traditional CSPM might run an API scan of your AWS environment every 12 or 24 hours to check if any S3 buckets were accidentally made public or if a security group port was open to the internet.
But if a junior developer accidentally makes a bucket public at 9 a.m., and the scan doesn't run until 9 p.m.?
An attacker has 12 hours of exposure.
And let's be real, attackers use automated scanning tools too. They monitor certificate transparency logs and scan massive IP ranges constantly. They will find that public bucket in minutes, not hours.
Exactly. Event-driven architectures change this dynamic from reactive to proactive. Instead of polling, you stream your CloudTrail logs directly into a message bus, like Amazon Event Bridge. The exact millisecond an API call is made, say, a put bucket ACL changing the policy to public event bridge, sees that log entry.
And triggers a response.
Yes, it matches a rule you defined and instantly triggers a serverless Lambda function. That Lambda function evaluates the change, realizes it violates your baseline security policy, and executes the API call to automatically revert the bucket back to private. You move from detection in hours to automated remediation in milliseconds.
That is the gold standard for posture management. But let's look at the worst-case scenario. What happens if the attacker manages to acquire highly privileged administrative credentials? What if they realize they are being monitored and they try to cover their tracks by simply deleting the CloudTrail logs or wiping the log analytics workspace?
That brings us to the fundamental principle of immutability and chain of custody. If you cannot trust the integrity of your logs, you cannot prove what happened. It is an absolute, non-negotiable requirement to use worm storage right. Once, read many. In AWS, this means streaming your logs to a dedicated, heavily restricted S3 bucket in a separate logging account and configuring that bucket with S3 object lock.
And there's an important distinction there between governance mode and compliance mode, right?
Crucially important. If you use governance mode, an administrator with specific IMM permissions can still bypass the lock and delete the files. But if you use object lock in compliance mode, it is mathematically enforced at the storage layer.
Meaning no one can delete it.
Once a log file is written, it cannot be modified, overwritten, or deleted by absolutely anyone, not the root user of the account, not even AWS support, until the defined retention period expires. This guarantees forensic integrity. Even if the entire production account is compromised by an insider threat or a highly privileged attacker, the audit trail remains completely pristine.
Okay, so we have highly normalized, immutable logs streaming in real time. We're catching control plane API calls and data plane access events. We're using event-driven architectures to remediate misconfigurations. But here's the terrifying reality about worm storage and immutable logs. They only record what the operating system tells them to record.
This is the crux of the problem.
All of these logging agents, these sidecars, these monitoring tools, they operate in what we call user space, ring 3 of the operating system architecture. And sophisticated attackers, advanced persistent threats, they know exactly how to manipulate user space. If they exploit a vulnerability, gain root access, and deploy a sophisticated kernel-level rootkit, they can intercept the data before it's logged.
They can hook the system calls.
Exactly. They can lie to your monitoring agents, making their malicious processes completely invisible. Your immutable log is just a permanent, mathematically verified record of a lie.
Exactly. If the kernel itself is compromised, or if the attacker is operating below the visibility of the user space agents, your standard host intrusion detection systems are completely blind. They will report that everything is fine while the server is being drained.
So to stop that, we have to bypass user space entirely. We have to drop down into the core of the operating system itself. Welcome to Part 4, the eBPF kernel revolution.
This is the absolute frontier of cloud-native infrastructure and security. eBPF stands for Extended Berkeley Packet Filter. Despite the old name, which sounds like it just manages firewalls, it has evolved into something far more profound. eBPF allows you to run sandboxed, highly efficient, and secure programs directly inside the Linux kernel itself, ring 0, without needing to write custom kernel modules, without modifying the kernel source code, and without rebooting the system.
Let's refine an analogy to really visualize why this is so powerful. Think of traditional security agents, like your antivirus, your log shippers, your SIEM forwarders, as security guards checking badges in the lobby of a massive bank building. That's user space. They can see who asked to come in, they can check IDs, they can monitor the public hallways. But if a master thief sneaks past the lobby, climbs through the HVAC system, or disguises themselves perfectly to bypass the guards, the lobby security is useless.
Right, because the guards only see what passes through their specific checkpoint.
Exactly. eBPF is fundamentally different. eBPF is like wiring the bank so that the building itself is the security system. The vault door itself, the cash registers, the individual light switches, and the network cables instantly report the exact millisecond they are touched. You aren't relying on a guard to observe an action. The mechanism itself is generating the alert. Every time a process opens a file, allocates memory, or opens a TCP network socket, the kernel has to execute a system call. eBPF allows us to attach microscopic sensor programs directly to those system calls. You cannot bypass it because it is baked into the very fabric of the operating system.
It provides the absolute unvarnished truth. The kernel cannot lie about what it is executing, because every application, whether it's a legitimate database or a malicious rootkit, eventually has to ask the kernel for resources. And as we look at infrastructure in 2025 and 2026, eBPF is no longer an experimental, bleeding-edge technology reserved for kernel hackers. It has gone completely mainstream.
Yeah, AWS really pushed it forward.
They did. The most significant indicator of this was when AWS made Cilium, which is an eBPF-based container network interface, the default networking standard for their massive Elastic Kubernetes service, EKS. eBPF is now powering entire product categories across modern infrastructure.
Our research breaks down 4 major cloud-native applications of eBPF. Let's walk through them, starting with networking, specifically focusing on projects like Cilium. Why is eBPF replacing traditional Linux networking?
It really comes down to scale and performance. Traditional Kubernetes networking, like kubeproxy, heavily relies on iptables to route traffic between pods and services. But iptables was designed in the 1990s. It processes rules sequentially. As a Kubernetes cluster grows to hundreds of nodes and thousands of pods, the iptables rules become massive linear lists.
And processing that takes time.
A lot of time. Every single network packet has to traverse this massive list, an ON operation, which causes severe CPU overhead and massive latency spikes.
Right. The CPU is spending more time figuring out where the packet should go than actually doing compute work.
Exactly. Cilium bypasses iptables entirely. It uses eBPF to process network packets directly in the kernel, often hooking at the XDP or express data path layer, which is right at the network interface driver level before the packet even reaches the standard Linux networking stack.
So it's incredibly fast.
Unbelievably fast. It maps IP addresses to Kubernetes pod identities instantaneously using highly efficient O1 hash tables. This architectural shift improves network throughput by 30 to 40%, drops latency drastically, and saves massive amounts of CPU cycles.
That is a staggering performance gain just by changing how the kernel handles packets. The second major application is observability, using tools like Pixie or Hubble. And the holy grail buzzword here is zero instrumentation.
This solves a massive headache for site reliability engineers. Traditionally, if you wanted to trace an HTTP request as it hopped between a dozen microservices to figure out why a database query was slow, your developers had to manually modify the application code. They had to inject tracing libraries, recompile the app, and redeploy it. Alternatively, you had to inject heavy sidecar proxies next to every single container.
Which introduces its own latency and management nightmare.
Exactly. With eBPF, you don't do any of that. Because every network request, every read-write operation has to pass through the kernel's network stack and syscall interface. eBPF programs using kprobes and trace points can simply observe the traffic directly as it flows through the kernel.
So it just watches everything automatically.
Yes. It automatically tracks all syscalls, HTTP requests, gRPC calls, DNS queries, and database payloads without modifying a single line of application code. You simply deploy the eBPF agent to the Kubernetes node as a daemon set, and instantly you have a complete real-time topological map of your entire microservice architecture.
That is a developer's absolute dream. No more fighting with development teams over injecting Jaeger tracing libraries or managing dependency conflicts. The third application builds directly on this capability, the evolution of the service mesh.
Yes. Projects like Istio are undergoing a massive architectural shift toward an ambient mesh. In a traditional service mesh, you deploy an Envoy sidecar proxy into every single pod. If you have 5,000 pods, you have 5,000 proxies.
That's sidecar bloat.
Exactly. It consumes massive amounts of memory and CPU across a large cluster. The ambient mesh architecture uses eBPF to intercept traffic at the node layer instead of the pod layer. This still provides the crucial service mesh capabilities like mutual TLS encryption, advanced layer 7 routing logic, and circuit breaking, but it completely removes the massive memory overhead of injecting sidecars into every pod.
The fourth application is where my security heart beats the fastest. This is the culmination of everything we've talked about, runtime security. Tools like Falco, which is an incubating CNCF project, and Tetragon. How exactly do they leverage eBPF to stop threats?
This is where we see a qualitative fundamental leap in defense capabilities. Falco uses eBPF to deeply monitor system calls across the entire node. It uses a rules engine to detect behavioral anomalies at the lowest possible level.
Give me an example of what it looks for.
Sure. For example, it can detect if a web server container suddenly tries to spawn a bash shell, or if an unexpected process attempts to read the etc shadow password file, or if a container attempts to mount a sensitive host directory. It detects these threats in real time by reading the raw syscalls, making it immune to user space obfuscation.
But detecting a threat is very different from actually stopping it. And this is where we have to highlight the critical architectural difference between detection and enforcement.
Exactly. Falco is incredible at detection. But traditionally, when it detects a malicious syscall, it generates an alert, and it passes that alert up to user space to be handled by a CM or a response engine. Tetragon, which is developed by Isovalent, the team behind Cilium, takes it a massive step further. They do active enforcement directly in the kernel.
How does that work in practice?
Tetragon can hook directly into the kernel execution functions, like sexexe, which is the syscall responsible for executing a new program. If Tetragon's eBPF policy detects a malicious process attempting to execute, say, an attacker exploiting a vulnerability to launch a reverse shell, it doesn't just generate a log and wait.
It takes action.
Yes, it can issue a sigkill command and terminate the process at the kernel layer in milliseconds before the attacker's binary even begins to execute in user space.
That is the absolute game changer. It solves the time of check to time of use race condition. It beats traditional host intrusion detection systems because it doesn't wait to write an audit log, pass it to user space, have an agent read the log, realize something bad happened 2 seconds ago, and then try to send a kill command. The kernel itself acts as the immune system, destroying the pathogen the exact millisecond it tries to replicate.
It fundamentally shrinks the window of compromise from minutes or seconds down to microseconds. It is proactive security baked right into the operating system.
Okay, I have to play devil's advocate here. I always get nervous when a technology sounds like absolute magic. Faster networking, zero instrumentation observability, sidecarless service meshes, and instant kernel-level threat termination. What is the catch? Why isn't every single enterprise running everything exclusively on eBPF right now?
Because there are very real, complex limitations that infrastructure and security teams need to be acutely aware of. First is the kernel version dependency. eBPF is constantly evolving. Many of these advanced features, particularly the sophisticated network hooks and ring buffers required for high-performance telemetry, require a modern Linux kernel, typically version 5.8 or higher.
And a lot of enterprises are not on modern kernels.
Oh, absolutely not. If you are a large enterprise running massive legacy systems like older CentOS 7 or RHEL 7 machines that are permanently stuck on kernel 3.0, you are completely out of luck. You cannot use these tools without undertaking a massive project to upgrade the underlying operating systems across your fleet.
And upgrading kernels across a massive production enterprise fleet is never a trivial task. It requires extensive regression testing. What else? What happens when things break?
The debugging difficulty is extremely high. Writing, troubleshooting, and maintaining eBPF programs requires deep, highly specialized knowledge of C programming, LLVM compilers, and intimate familiarity with Linux kernel internals.
It's not like reading a Java stack trace.
Exactly. If a traditional user-space Java application crashes, you get a nice readable stack trace. If an eBPF program misbehaves or a policy is written incorrectly, diagnosing exactly why a legitimate network packet was silently dropped at the XDP layer or why a critical syscall was blocked requires highly advanced platform engineering skills.
I imagine the ecosystem is a bit of a Wild West right now, too, as vendors scramble to implement it.
It absolutely is. We are seeing significant ecosystem fragmentation. You have Cilium, Calico, Falco, Tetragon, Datadog all utilizing eBPF, but implementing it in slightly different ways, hooking into different kernel functions. While standardization efforts are underway within the CNCF, there is functional overlap and sometimes severe compatibility friction if you try to stack multiple competing eBPF tools on the exact same Kubernetes node. They can conflict over who owns a specific kernel hook.
And what about the security of eBPF itself? To load a program into the kernel, you need massive privileges, right?
Yes. While the eBPF verifier ensures that a program is safe, meaning it won't crash the kernel, it won't enter an infinite loop, and it only accesses allowed memory, the deployment process requires elevated privileges, specifically the CIPPF or capsi-sedmin capability.
And auditors hate that.
They do. In highly regulated environments with strict compliance controls, granting these elevated privileges to observability or security agents can be a significant hurdle for security review boards. You're essentially trusting that the eBPF programs provided by the vendor are flawless. Because if a highly sophisticated malicious actor could somehow bypass the verifier and inject their own eBPF program, they would have ultimate, completely undetectable control over the entire node. They could intercept network traffic, alter file reads, and hide their own processes at the kernel level.
Wow. So to summarize this massive journey we've been on today, we started by looking at the hard, painful lessons of the real world. Capital One taught us that SSRF vulnerabilities paired with over-permissioned IAM roles and permissive IMDS architectures are deadly. Storm 0558 proved that the cryptographic foundations of identity providers are not infallible, and deep, anomaly-based telemetry is our only lifeline when the perimeter fails. Snowflake demonstrated that without enforcing basic identity hygiene like multi-factor authentication, your advanced cloud perimeter means absolutely nothing against commodity info stealers.
Then we evaluated the hyperscalers, mapping their tools to these exact threats. We saw that AWS offers unmatched granular control, mature hardware security modules, and global compliance scale. Azure dominates the multi-cloud CSPM visibility space and offers deep enterprise SIEM integration with Sentinel. And GCP excels in zero-configuration default encryption, strict privacy boundaries, and petabyte-scale AI-driven data analytics with Chronicle.
We dove into the telemetry lifeline, establishing that distinguishing between the control plane and data plane is vital for cost and visibility. We saw how normalized, event-driven, and mathematically immutable logging via CloudTrail Lake, log analytics workspaces, and the OCSF schema is the absolute prerequisite for any functional SOC. And finally, we plunged deep into the Linux kernel itself, uncovering how eBPF is fundamentally rewriting the laws of physics for networking scale, zero instrumentation observability, and microsecond-level runtime threat enforcement with tools like Cilium and Tetragon.
When you step back and look at the evolution of the security professional over the last decade, it is truly staggering. Just a few years ago, we were manually gripping static text logs and fighting with massive, fragile IPTAbles rule sets. Today, we are architects of event-driven multi-cloud ecosystems. We are leveraging generative AI to parse complex, normalized schemas, and we are deploying kernel-level enforcement policies that instantly kill threats in microseconds. The tools have become unimaginably powerful, but they demand a much deeper architectural understanding of how systems actually function beneath the surface. You can no longer just manage the console, you have to understand the kernel.
Thanks for tuning in to InfoSec Bytes. Keep exploring our 100-plus episodes on information security, AI, cloud, quantum, and cybersecurity incident root cause analysis. Please like, subscribe. We are on various platforms like Spotify, Apple Podcasts, YouTube, Amazon Music, and share to stay connected and keep your cyber defenses strong. See you in the next episode. Stay tuned.
But before you close the app, I want to leave you with one final, slightly terrifying thought to mull over as you review your cluster architectures this week. If eBPF allows us to observe and kill malicious processes at the absolute lowest kernel level in milliseconds, what happens when advanced persistent threats stop trying to evade the monitoring and start designing malware that specifically targets vulnerabilities within the eBPF verifier itself? If the security guard is the building, what happens when the attacker learns to control the concrete? Are we just moving the ultimate battlefield one layer deeper into the machine? Think about that.